All right, well, it's 1 o'clock, so we'll get going. We've got just a little bit left to do today on SN2 versus SN1. We're not going to do elimination on the exam. I'm going to remind you at a couple of points through the lecture today that there's a hole out there we're going to fill with elimination information, but you won't need that uh, for this exam. As I said last time, the exam is available tomorrow. The time limit is 3 hours like last time. It is 25 questions, and I think they're all fair, but if you see any typos, feel free to let me know. I can change those in real time. Does anybody know from experience what Learning Suite recommends if you're in the middle of an exam and suddenly Learning Suite dies? Do they stop the clock for you, or they don't? Okay. I think they recommend if you're in that situation, not closing the browser tab because I think that potentially pauses things. If you get into trouble, just email me and I'll see what I can do. My intent, though, I will warn all of you, is not to have you take the exam twice. So if it shows up and says you can take it twice, it's because of some poor souls among you who have gotten locked out and need back in. So don't waste your time. It is all multiple choice, yes. Yeah. So let's deal with the remaining SN2, SN1 issues, and then we'll do some practice where we consider whether a particular outcome is SN1 versus SN2. So we wanted to deal with stereochemical consequences of the SN2 reaction. And this is a nice time to review stereochemistry issues as well. We've done some of this last lecture, but we're going to dig in just a little bit deeper based on some good questions I got in office hours today. Remember that for the SN2 reaction, if a starting material is chiral, and if the leaving group is at a stereocenter, the nucleophile must attack from the backside. And let's just say what the nucleophile is. This is going to be a good nucleophile. We'll say it's A side. The nucleophile must attack from the backside, which means we get switching or inversion of stereochemistry. We have to be a little bit careful with the term inversion. There are terms that we use so there are two kinds of stereochemical terms. You have absolute terms, which are R versus S, or E versus Z. What the heck is that? Z. And then you have relative terms, and there's a lot more of these than we've even encountered yet. It could be up versus down. Up relative to what? Down relative to what? Cis versus trans. Same versus opposite. And inversion is one of these relative terms. That means the stereocenter was one way, and then it switches to the other way. You can't say that, if the stereocenter is R, it's going to always switch to be S. That's true here. But if our nucleophile was something that was very low priority, I can't imagine sort of what that would be, but it might you might find a situation where the stereocenter stayed R, even though there was an inversion of configuration. So I want you to understand that inversion happens because as the nucleophile approaches, well, just what we talked about last time, as the nucleophile approaches the carbon that, sorry, I keep finding myself saying the words, the carbon that has the leaving group. And that's a lot of syllables, and I'm tired of saying it, so we're going to abbreviate that today by calling that the alpha carbon. and we'll use Greek letters to talk about distance away from that alpha carbon. So anyway, we used to have chloro up at the alpha carbon. Now the nucleophile comes in and is down. And last lecture we'll show you why that is. That is because as the nucleophile comes in, it pushes the three other groups at the alpha carbon away from it. So that's important for you to know and master. Notice that the product is chiral as well. And we only get one enantiomer, none of the other enantiomer. Okay? So that's important, because if you get that wrong, that means you don't understand the mechanism of the SN2 reaction. A few words about drawing products that may be informative to you. We haven't necessarily talked about this, and it's come up a couple of times in office hours. If I draw a molecule like this, that means that I give you no stereochemical information, either relative or absolute, about the stereocenter. Only connectivity information. So if I draw a molecule that way, you must assume that I mean both enantiomers. Alternatively, if I want to indicate both enantiomers, I could draw just one of the enantiomers and then have a little plus or minus in parentheses. That is a holdover from the characterizing enantiomers by optical rotation. You know enantiomers rotate light by the same amount but in opposite directions, plus for one of them and minus for the other. So the plus minus in parentheses means you have a 1-to-1 mixture or a racemic mixture of both enantiomers. So if you were to draw the product this way, that would be incorrect, because it doesn't convey that you get only one enantiomer, and it doesn't indicate the correct enantiomer that you should get. Questions so far? Okay. So we've talked about SN1 and how you go through a planar carbocationic intermediate that can be attacked from above or below. And at first, you may have thought there's actually not that many stereochemical issues to deal with here if you have a starting material that is not chiral, and you do the SN1 reaction, and that leads to an intermediate, a carbocationic intermediate, which is also not chiral. There is no stereocenter in that molecule. It is its own mirror image. The LUMO, as we've talked about before, is the empty p orbital that's evenly distributed on either side of the carbocation, and that can be attacked from either above or below, though it turns out you can't tell which is which, because the product from above attack and below attack are not stereoisomers. They're actually the same compound. So if your starting material is not chiral in an SN1 reaction, the intermediate won't be chiral, and the product will also not be chiral. Now let's make it a little more interesting. Let's have the starting material be something that is chiral. So maybe let's use the same starting material as we used above, a secondary alkyl halide, only this time we're going to use a nucleophile that is not a good nucleophile, so it can't do SN2 and it will wait around for SN1. We'll review that later. The starting material is chiral. Let's draw the intermediate that comes from having the leaving group up and leave. What do you think about that intermediate? Is it chiral or not chiral? Okay. Okay, it does have 3 different groups on the carbon. Let's run our fail-safe test for chirality. Is it the same as its mirror image? It turns out I can flip this thing over, and you actually do have the same thing. So that molecule is actually not chiral because it is the same as its mirror image. And again, even though our starting material was chiral, we lost the stereocenter. The alpha carbon is no longer a stereocenter. And what that means is the nucleophile must be able to attack from above or below at the same, to the same extent. Another way of seeing this is to take a bird's eye view of this molecule and imagine looking down on the carbocation from above and imagining what you would see. Here is the top lobe of that empty p orbital on the alpha carbon. And then let's illustrate what it looks like from below. The only difference we see is in the sign of the wave function, but that makes 0 difference at all in terms of reactivity. The nucleophile sees the same thing from above or below, and that means the attack from above or below has to happen to the same extent. So my product from above has to form to exactly the same extent as the product from attack from below. Now, a couple of questions about the products that we have formed in this SN1 reaction. Are they chiral? Nodding our heads, sure. You can tell that because there's a stereocenter, though they have opposite configurations. Okay, what is then the relationship between these 2 compounds? What is the stereochemical relationship? They're stereoisomers. They got the same connectivity. They have opposite configuration at their one stereocenter. So what's the right word? Okay, diastereomer would be if they're not mirror images of each other. But if we drew a line here, that would be our mirror plane. So actually the word we want is the other kind of stereoisomer, enantiomers. Okay? Recall that enantiomers are mirror images of each other that are not the same. These molecules each have one stereocenter and they're opposite in configuration, and therefore they must be enantiomers. Enantiomers have the same chemical and physical properties, and that includes stability and rate of formation, anything that might influence the amount of one product versus the other. And so we have to form them in a 1-to-1 ratio. We have to get a racemate or a racemic mixture of enantiomers. If you go through a chiral intermediate, I'm sorry, let me start that again. If you go through a not chiral intermediate and you form a stereocenter, you have to form both configurations in equal amounts. If you go through a not chiral intermediate and you form a stereocenter, you have to form both configurations in equal amounts. The products will be enantiomers of each other, and they have to form in a 1-to-1 ratio. All right. Brennan, it looks like there's some discussions on seeing that two things are enantiomers. Can I be helpful there?
I think somebody can understand.
Okay.
Why wouldn't make
Okay, so we can do this really quickly. A question from the chat is, how are these actually different? Couldn't you just pancake flip this molecule from top to bottom, or from bottom to top, 180 degrees? If you did that, you would get this. It's true, but the ethyl group, which used to be in the front, will now be in the back, and the proton, which used to be in the back, will now be in the front, and those are not the same thing. So it may be that you were doing the, folks at home, one of you may have been doing, one or more of you may have been doing the pancake flip, but not remembering to switch the other groups when you did it. And yeah, if that's confusing, a model set can be helpful. All right, yes? Can carbocations ever be chiral? Statin, that's exactly where we're going next. It's a great segue, great setup for, thank you very much. Let's give that man $20, shall we? I don't actually have cash on me, so I'm sorry. He accepts Venmo, though. That's the counter excuse. Kids these days, when they come to your door selling stuff, you can't shoo them away by saying you don't have cash, because they accept Venmo now. So. But guess what? I don't have the Venmo app, so what are you going to do? Go ahead. Yes. Yeah, the question here in class is, is it true that if your starting material is not chiral, your intermediate is not chiral, your product is going to be not chiral? All right. So let's try a situation in which the carbocation, someone from home is plugging Bitcoin, but it's not Elon Musk, so we can't expect the price to increase any. All right, let's imagine a situation. In fact, there's a situation from your practice exam in which, and you may not have noticed this, in which the intermediate itself is chiral. So I'm going to try to remember this one. I might get it wrong in some of the details. This is a tertiary alkyl halide. So we know right away that SN2 is not a possibility. Let's... maybe we'll keep the same nucleophile as we've done before. I don't know. This is a good nucleophile, but you can't do SN2 because of the alkyl halide. So SN1 is your only option. So leaving group will leave. Now let's talk about how best to draw that structure. My starting material had two stereocenters. In my intermediate, the alpha carbon is no longer a stereocenter. So we have lost of information, loss of configuration at that alpha carbon. What about the carbon that's, I guess we'd call it the alpha, beta, gamma carbon? What about that gamma carbon? Does the leaving group leaving change that one at all? No, it's not participating in the reaction, so that one doesn't change. Okay, what effect does that have? Now look at this intermediate. Is that intermediate chiral or not chiral? The intermediate has to be chiral because it's got one stereocenter. It was chiral to start with, and it is, we haven't changed one of the stereocenters, and so it is chiral there, okay? And in fact, we can assign R versus S to this stereocenter, and we have to assure ourselves that no matter what we do in this reaction, that stereocenter is not involved, so its configuration has to stay unchanged. I'm just doing this in my head, and you can check me later on and see if I'm right, but we'll call that stereocenter R. To convince ourselves that this molecule is chiral, we could draw the mirror image, and if a molecule has one stereocenter, it must be chiral. So that's true for this molecule, so we sort of know it without even worrying about it. If we assign configuration of the mirror image, we would see instead that that stereocenter is now S. If we tried to pancake flip it over to try to get the methyl group on the same side of the molecule as it is on the left, on the other side of the mirror, sliding our spatula underneath that and flipping it over from left to right, that would switch the methyl group pointing now to the left, but instead of up, it would be down. And so there's nothing you can do, worlds without end, to make these two the same thing. And therefore that intermediate is chiral. All right, I'm going to erase that because, well, maybe I'll leave it there for just a second. All right, so if you're with me so far, that's a case where the intermediate could be chiral. Now let's think about the consequences of that. Let's imagine the nucleophile's view from the top face of this carbocation. And I'm going to draw the empty p orbital. And then I'm going to attempt to draw what a nucleophile would see from the bottom face. Anyway, if we were looking up from the bottom face, what I'm trying to tell you is we would see this. And if you don't believe me, you can go home and pretend to be looking up at the creepy blue boy's face through the encyclopedia or something like that. This is irreverent, but I guess I'm going to say it anyway. My dad likes to laugh that Tom Hanks plays all the parts. So you've got Tom Hanks the father, Tom Hanks the son, and Tom Hanks the hobo ghost, which is the trinity of Tom Hanks. I'm going to be done with the Polar Express now, but anyway, let's examine whether, how much time did I spend? Let's examine whether the nucleophile for this chiral intermediate sees the same thing above versus below. What differences do you detect? Imagine approaching the structure on the left. You're saying steric hindrance because of the methyl. Yeah, the nucleophile coming from above would see a methyl pointing towards it. From below, the methyl would be pointing away with a proton towards it. So perhaps the pathway on the left is more hindered than the pathway on the right. We don't know whether one would be more favorable than the other. I might predict that the one on the left the one on the right approach from the bottom might be faster. We don't really have to decide that. We just know they're different. The two faces, the top face and the bottom face, are different. And that means they don't have to happen to the same extent. Attack doesn't have to happen to the same extent. That's what I mean. They don't have to be attacked to the same extent. So our product for as the nucleophile comes in, and I forget what we said it was going to be and don't even care anymore, attack from above would put the nucleophile on top and on the same side of the molecule as the methyl group on the gamma carbon, whereas attack from below, excuse me, would put the nucleophile, on the opposite side of the molecule as the methyl group on the gamma carbon. What is the stereochemical relationship between those two molecules? I'm hearing some whispering to yourselves. I'm hearing diastereomers. That's right. The stereocenter here in purple for that gamma methyl group doesn't change. However, the stereocenter at the alpha carbon does change. They're different at 1, but not all. They are stereoisomers, but not mirror images. Therefore, they are diastereomers. And recall that diastereomers have different chemical properties, including stability and rate of formation. So they don't have to form in a 1-to-1 ratio. All right? So what about that? Who cares about that? Well, it's going to be useful to you in the future as reactions get more complicated to be able to tell whether predicted products are enantiomers of each other versus diastereomers. Because if they're diastereomers, there's a chance that one could be major versus minor, and that might be useful. In this case, we don't really know, and I wouldn't expect you to predict it, but you should recognize them as diastereomers and be comfortable with the fact that they don't have to form in a 1-to-1 ratio. Yeah? Do we need to understand how to do R versus S if the lowest priority group is planar? And the answer to that, I think what you're asking is from the practice exam, did you like assigning stereocenters in morphine? That was fun. The problem, I think, was this central stereocenter here, where if you've done this problem and you assign the priority groups, maybe I'm wrong. No, I think I'm wrong there. An example of the situation I think you're talking about might be where a priority 4 group is pointing to our left instead of up or down. Yeah. Two ways to deal with that situation, but probably the easiest is to imagine your eye here looking down the carbon-hydrogen bond so that you can't see the hydrogen in the back. Chloro would be up, and if you're laying down in the page and looking at that molecule, the methyl group would be here, and the ethyl group would be here. Knowing that the lowest priority group is in the back, then assigning R and S is like that. So that may be the best way to do those kind of problems. Couple of things about drawing the answers to these questions now that we've done some of this. If I wanted to convey that the product of this reaction gave me 2 enantiomers, I could draw the products as I've drawn them over there, or I could draw both enantiomers, or I could draw, or I could draw just one enantiomer with the plus and the minus, Or I could draw no dashes or wedges whatsoever, and that communicates that both configurations are possible at that stereo center. That's just fine. In contrast, if I'm not careful, I can make a mistake down here. So suppose I try to draw just one of the two stereoisomers on the left, or on the right. I'm drawing it on the left if they were on the right. Good golly. And suppose I put a plus or minus there. Are these two the same thing? No, because if I use the plus or the minus, what does that communicate? That means enantiomers. So I would have this one and its enantiomer, which would be and that's not what we're about at all, right? We've changed the stereocenter on that methyl group. We said at the beginning it was R, and it's not involved in the reaction, but if we use the plus or minus, we communicate that, oh, it does change. So that's a problem. This is incorrect. Another problem would be to draw the molecule this way for the same reasons. You mean both configurations there and both configurations there. So this would mean the four stereoisomers, both diastereomers and their enantiomers. So this is also incorrect. The correct way, if you wanted to simplify, it would be okay to keep the R stereocenter there and draw it out, but then to use no dash or wedge at the other one. This would communicate that the methyl stereocenter stays the same, and the stereocenter at the alpha carbon, you got both varieties. Yes?
How do we know how much of each one is going to count if it doesn't have to be one?
How do you know? Good question. If which one will be the major one if it doesn't have to be one-to-one? You might not, but there might also be principles that you could use to make a prediction. So this is beyond the scope of what we want to do on this exam. We predicted that it would be faster to attack from below than from above because of steric hindrance of that methyl group. However, we didn't consider the fact that that these are cyclohexanes and the products might differ in stability too, depending on the conformations, right? You got two methyl groups, and then whatever this nucleophile is, maybe it prefers to be equatorial versus axial, depending on its size relative to the methyl groups. So we might not actually know. There are some reactions that are controlled by what forms fastest, and there are other reactions that are controlled by which is the most stable product. That's a difference. We don't need to worry about it now, but we'll come back to it later. So the answer is we're going to be able to make those predictions for this particular example. All I ask is that you realize that they don't have to be one-to-one. Yeah. Yes, this example that we've just done gave you diastereomeric products because the intermediate was chiral. Yeah. All right. Now that, I think, is as complicated as the stereochemical issues of SN1 and SN2 get. Mastering these issues is important not only for this exam, but because reactions are going to continue to increase in complexity, and demonstrating mastery of the mechanisms of those reactions is going to continue to depend on how you deal with stereochemistry. So these skills are going to come up again and again and again. All right, so we've got some time maybe to do some examples, maybe some practice. And want to give us a chance to sort of think about whether reactions, given a starting material, whether you should predict a reaction would proceed through SN1 versus... All right, so I want to put it all together now. And with some various examples, we're going to consider just the substitution products and just whether we're going to observe SN1 versus SN2 products. So I'm going to make some stuff up. Maybe. Anything good in here? These are my notes from last time. Or no, from a year ago. I don't know if there's anything good in here. What are we going to do here? Let's go ahead and do... no, I don't really like that. I want to do Cn minus. Let's predict what's going to happen. And I always start by considering the alkyl halide and what the substitution pattern is. It's going to be useful for us eventually to talk about carbons. I've noticed that in lecture I've been saying a lot, the carbon that has the leaving group, and that's a lot of words. So we're going to call the carbon that has the leaving group the alpha carbon. We're going to define that here, equals the carbon that has the leaving group. Cool. My ringtones are not that cool. In fact, the ringtone for my mother is the Death Star alarm going off, because I figure when she calls, I better answer. Amber's ringtone is Yoda laughing, because that's kind of fun. It used to be the Minions going Beto, 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 but I found that to be kind of annoying, and I would be kind of grumpy by the time I pressed answer, which was not good for our marriage, so I reassigned the ringtone. Okay, so this is a secondary alkyl halide. The substitution of the alpha carbon is secondary. What do we know about that? What do we know about the rate of SN2 for a secondary alkyl halide? Slower, but possible, right? So we're considering SN2 slower, but okay. And then how about the rate of SN1? It's not as good as a tertiary alkyl halide, but probably possible. So that's good. As Jack Sparrow once said, that's even less than maddeningly unhelpful. But at least we know what our options are. So go ahead. Secondary alkyl halide, because if you look at the three other things besides the leaving group that are attached to the alpha carbon, two are other carbons, and the other is a hydrogen. Yep. For primary, it would just be one non-hydrogen thing, tertiary, all three. Yeah? A question, I think, and it's going back a little bit, would you need to know how protons transfer in SN1 reactions? I think I can answer that pretty quickly. In the example we did before, our nucleophile was ethanol, but you notice there used to be a proton on the ethanol, so what the heck is going on? The practice exam shows you an intermediate that looks like this. You've just formed a new carbon-oxygen bond between the lone pair electrons on ethanol and the positively charged carbon. So now the ethanol oxygen is attached to three things and is necessarily positively charged. That's good enough, but what actually happens in solution is whenever you use ethanol as a nucleophile, likely it is also used as the solvent and is present in vast excess. Okay? So what can happen next is a simple acid-base equilibrium in which the proton is transferred from the positively charged oxygen on our molecule that we're interested. Oh, what the heck am I doing? That's, I don't know, that's just a methyl group there. From the positively charged oxygen that's on our interesting molecule to the oxygen of ethanol. Simple proton transfer reaction. If you want the arrows, lone pair from oxygen pulls the proton off and electrons go back on the other oxygen. This is acid-base chemistry, and to predict the position of this equilibrium constant, you would need to know the pKa's of the acids on either side of the equation, and they're about the same. So the equilibrium constant may or may not be close to 1, especially if we have a crazy large amount of ethanol. It might actually push the reaction to completion, and in any case, we know that removing the proton is reasonable. That's the product. Now, I'm never going to show you these two options and try to trick you and say, is this the product or is that one the product? Because that would be pointless. Yeah. Yeah, so this is a good question too. Your text sometimes, or actually all the time, shows the leaving group, whatever it was, I forget, coming in and removing the proton. If you did that, the acid on the other side of the equation would be HBr with a pKa of -9, so that looks a little bit less likely to me. It's not technically wrong because your book shows it and therefore it must be right, but a more reasonable thing is probably what I've shown you. I won't give you both options in a mechanism question and try to trip you up, unless the question is about pKa, in which case you should be able to work your way through that. All right. Yes, so secondary alkyl halide, we've got nothing so far as to whether SN1 versus SN2 should dominate. So we have to look to the nucleophile. So CN- would be on our list of good nucleophiles. Its conjugate acid is HCN. And if you look it up, that has a pKa of around 9. So that's pretty respectable. And therefore, in terms of substitution reactions, good nucleophiles don't wait for SN1. Okay? They're reactive enough that they go ahead and do SN2 if possible. We've already said that SN2 is possible, therefore, the reaction should be SN2. Now, I happen to choose a starting material that is not chiral. So we can't actually tell whether in our product that we draw, we can't actually tell whether this was attacked from above or below. But I was thinking of it on the fly, so let's just put something else on there so that there is a difference. I don't know. Let's slap a, I'm tired of methyl groups. Let's slap an ethyl group on there. Now, if I draw the product and I mean for it to be SN2, where do I need to put CN- on that alpha carbon? Up or down? Down. Good. Okay, so that's one way, that's how I would approach this kind of problem. Now let's change it to SN1 just by changing the nucleophile that we're using. Let's use water. Water is a poor nucleophile, and poor nucleophiles don't do SN2. They're not reactive enough. They have to wait for the leaving group to leave. So, showing you only the substitution product, if you want, if you've determined that it's SN1, it can be helpful to draw the carbocationic intermediate with the positively charged alpha carbon, because that can help you remember that that thing can be attacked from above or below. So our nucleophile is water. I'm not going to show the last proton transfer step. I'm skipping ahead to the final neutral product. And those two would be the SN1 product. One from above attack, one from below. Let's see how much you've learned in today's lecture. Are those products required to form in a 1-to-1 ratio? Not in this case, because they are diastereomers. Good. Somebody's suggesting, let's say our conjugate acid had a pKa of 2. Would SN2 still be favorable? Is any pKa above 0 considered a good nucleophile? I can't think of anything off the top of my head that has a pKa of 2 other than an amino acid. So let's go there. An amino acid is a carboxylic acid that has an amino group adjacent to the carboxylic acid. The problem with doing what we want to do here is that the nitrogen is also nucleophilic. This is a molecule with 2 nucleophilic groups. I said nucleophilic. I did not say nucleophilic. You will never hear me say nucleophilic, even though nuclear is an accepted pronunciation of the word nuclear now. That started when you were very young in the days of ex-President George W. Bush, and it was somewhat endearing, I guess, from him, but then became grating from other people. But now it's okay. I'm sorry. In any case, we would never do an SN2 reaction on this molecule alone because we'd have to worry about whether you react with that oxygen or that one. I'm going to tell you something that you don't need to worry about. One thing we do with this nitrogen is we attach a group to it that prevents it from being a good nucleophile, but can later be removed. And that group looks something like this. It's called a protecting group. You don't need to worry about it. I'm basically talking to myself and convincing myself it's okay to give you this example. That protecting group has a nickname. It's called Bach. And so most people will write the structure of the amino acid like this. Don't worry about it. If we wanted to do an SN2 reaction on this, the pKa of the conjugate acid of an amino acid, let me just draw that structure, would be around 2. It's lower than the pKa of a normal carboxylic acid because of the electron withdrawing effect of the nitrogen, the inductive withdrawal of electron density. In any case, yes, you could use an alkyl halide and do an SN2 reaction. This is a good nucleophile, and this electrophile is a methyl halide, which, you know, SN2 is great, SN1 is a no-no, and therefore the product would be the corresponding substitution product, where we swapped out this whole thing for the iodide. So yeah, anything that's basically above pKa of 0, you're good to go as a nucleophile. SN1 was not acceptable for this case because it would require going through a methyl carbocation, which is too unstable to form in solution. By the way, why is that? Why is a methyl carbocation less stable than, say, the tertiary carbocation? Hyperconjugation, the answer to everything, but then now convince me you know what that means. That sounded more accusatory and adversarial than I intended it. I apologize. Would you please expand on that?
The spreading out of electrons via empty orbit.
Right? You've got, again, let's call the carbon in the middle with the positive charge the alpha carbon. The key is, do you have any carbon-hydrogen bonds on the beta carbon? Because those filled carbon-hydrogen sigma bonding orbitals can overlap with and mix with the empty p orbital to give you a spread out LUMO. And then this is the thing that's favorable, spread out lower energy electrons from the CH bond. Yeah. So yes, the methyl carbocation doesn't have any beta protons. There's no alkyl groups attached to that alpha carbon, and therefore it's too unstable to form as an intermediate. All right. Other questions? Yeah? Just to clarify, there will be nothing about elimination on the exam. Let me think. Question 1. Question 2. I'm sorry, I'm just messing with you. No, there isn't. Knowing about elimination reactions shouldn't need you shouldn't need to know that for anything on the exam. And if it does show up, I will fix it. I don't think I've done anything on purpose. There's always a chance that I did something intermittently, but I can change it if I did. So one question that's kind of interesting is, what if you have what if you have like a methyl or a primary alkyl halide and a weak nucleophile as your reactive material? For our purposes, we're going to pretend like no reaction happens. In reality, that will depend on really how reactive the alkyl halide starting material is. So it turns out that for reasons you should understand, iodide is a better leaving group than bromide, which is a better leaving group than chloride. So CH3Cl probably doesn't react at all with water. The methyl iodide, it turns out, is probably water sensitive. It is reactive enough that it can do SN2. But for our purposes, if you have a combination between a weak nucleophile and a methyl or primary alkyl halide, we'll say nothing happens. So in previous semesters, students have found it may be useful to map things out in a table. This was back when they were taking exams in the testing center and felt they had to memorize things. That's a little bit less applicable to you. And the table will be incomplete because there's other things that can happen. We're not dealing with elimination reactions. But you know, it's useful to consider what can happen in each of these categories. For example, a good nucleophile with a methyl or primary alkyl halide will go ahead and do SN2. It'll do that with a secondary alkyl halide too. For a tertiary alkyl halide, you can't do SN2, so, oh man, so you have to do SN1 instead, even though it's a good nucleophile. For a poor nucleophile, we're going to say probably no reaction for primary and methyl alkyl halides, though we'll put an asterisk on that to indicate that that's probably an oversimplification. In contrast, a poor nucleophile with SN2, probably a poor nucleophile won't do SN2 because it's not reactive enough. It will wait and then do SN1. And then, of course, for tertiary alkyl halides, there's also no SN2, so SN1 is your option. And you can organize things in that way, and that can help you predict products in a reasonable way. Now, we're going to make this more complicated in the next couple of lectures because we're going to start talking about something else that can happen to these alkyl halides, elimination, And whether or not that happens will depend on whether our nucleophiles are also good bases. But that's a story that's complicated enough that I think we'll leave to another time. So with that, have a good weekend. I laugh to myself because you'll be taking my exam. So may God have mercy on your souls, I think is the appropriate phrase. Good luck, and we'll see you Monday.
Dr. Price.